Hey everybody, thanks for tuning in. Today we're going to be starting a brand new lecture series, transitioning into talking about stars now. So it turns out that we actually know a great deal about how stars work, which is kind of surprising considering that they're so far away, literally light years away from us. So I think it's worth asking the question of, if something is so far away, then how can we study them, right? And so in this topic, we're going to be discussing some methods that we use in order to study stars. And what you're going to discover from learning these methods is that the observations that result from these methods is going to be what's going to drive what we know about stars. All right, so let's just jump right in here. So what can we measure from stars? So this is a picture of a star taken by the Hubble Space Telescope. And unlike the pictures that you see typically on the internet, this looks kind of nothing like that. After all, it is black and white, right? And so typically when you see data from the Hubble Space Telescope, it'll look like this. It's going to be your unprocessed image. And so you kind of have to do a lot of massaging to this picture to get it to look the way you would do in the internet. But from a researcher's perspective, we're not looking for aesthetics, we're looking for information. And that information is kind of encoded in the pixels from this image, which is what we're really interested in if we're studying the properties of a celestial object like stars. So from an image, what can you measure, right? There's a lot of information you can take away just from looking at a picture. So for example, if you were able to set up some sort of coordinate system, basically like every pixel would correspond to a location in space, then you can measure, the relative positions of these stars. Where are these objects in the sky? Okay, and then we can also hover basically like our cursor here on every single pixel in this picture, and then that will return some sort of numerical value, and that value will correspond to a brightness. Okay, so you will be measuring the brightness from an image, and then depending on what kind of filter you've used in front of your telescope, let's say it's like a red filter, a blue filter, and you measure the brightness comparing filter to filter. Like, was this star brighter using a blue filter, or was this star brighter in the red filter? Then you can get a sense of the true color of the star. Does this star actually appear red, or is this star actually more bluish if you were to go out into outer space and see the star with your own eyes? Of course, I would not recommend that because the star is really, really bright in general. So, you would just be using the data coming from the telescope to use that. So from those three things, you can basically get some intrinsic properties about the star. So for example, you can measure how far away these stars are just from comparing their relative positions in different times of the year. And that's actually what we're going to be talking about specifically for this lecture. Okay? But other things, for example, brightness, because we know that brightness depends on the intrinsic luminosity of the star, and then two, if you can figure out how far away that object is, which is the distance, then you can get the luminosity of that star. Okay, so luminosity, or again, the amount of light that you can emit is obtained from the brightness and the distance, and then also the temperature of the star, how hot or how cold this star is. And again, that's going back to talking about the radiation laws, whereas the color or the wavelength of the black body curve that this black body curve peaks at will give you the temperature of that star's surface. And so you can also choose to take the light coming from that star and break it up into tiny little components, right? So you can choose to observe the spectra of that star. That's pretty much what you're doing. And so in this picture, I'm basically showing you 7 different spectra from 7 different types of stars that we'll eventually study. And you can see, depending on what kind of spectra you're looking at, the spectra looks slightly different. So for example, for the row that you're seeing as O, it's more of a continuous spectra. And then for the row that you're seeing as M, there's a lot of absorption lines there. And so it turns out that when you're observing the spectra of these stars, it's going to reveal a lot of information about their physical properties. And the wavelengths of these absorption lines, you can get the composition and also the type of star they are, which is something we'll also talk about later called the spectral type. All right? So this is giving you a slight preview and an overview of what's going to be coming in store in talking about the nature of these stars. All right, so first off, let's measure distance. How do we figure out how far away stars are? So in astronomy, it turns out that distance, or trying to figure out how far objects are in space, is actually one of the hardest things you can do. And the reason for why that is because when we look out into space, it looks like a two-dimensional projection. It doesn't look like a three-dimensional space to us. After all, we're just seeing like a black patch of sky with some pointy, bright dots layered on top of it. And so if you're seeing a bright object, you're not exactly sure is that object actually bright? Meaning, is that object actually emitting a lot of light? Or is that object actually just really close to you, but it's pretty dim in general, right? Because again, brightness goes down with distance. The further away you put something, then the dimmer it is, but the closer you put something relative to you, then the brighter it's going to be. And so it's very difficult to figure out how far away something is. And depending on what kind of object you're talking about, whether it's stars or galaxies, we have to resort to using different methods. So for this lecture, we're going to talk about how do we measure stars' distances from us. So the method that we use is the same method that our eyes uses for depth perception. So for example, we have two eyes, and if we place an object in front of us and we're looking at it with both of our eyes, if you place an object really close, and then imagine closing one eye like this, you see some sort of background relative to your finger, and then when you switch eyes, that background significantly changes. It shifts a little bit, okay? And so the amount of change that your background has shifted to will tell you qualitatively if an object is far away or close to you. Because imagine if you were able to place your finger really, really, really far away from you, then the background of your finger will not really change all that much. So therefore, you can conclude, qualitatively speaking, that if the background doesn't change that much, switching from eye to eye, then that means your finger is really far away. And when the finger is really close, if your background is changing a lot, then again, you can again say that your finger is near to you. And so if you look at this picture, it's illustrating the same idea. These two guys are basically looking at the same tree. And if this tree was close to them, this person will see a different background relative to this person. This person will see this background, whereas this person on the left will see this background on the right. Okay? But again, imagine if this tree was really far away, then these two guys will actually literally see the same background. Okay, so now let's apply this same idea in space. And just to define a few words here, by the way, before we jump into talking about space, the baseline is basically the separation distance between these two guys. Or if you're talking about the baseline on your eyes, it's going to be the separation distance between your two eyes. And it turns out, if you have a bigger baseline, then the better you are able to figure out how far away something is. And so the further away an object, the bigger the separation distance you need between your two eyes or these two guys trying to look at the same object. Okay, so now let's actually go into talking about how to apply this into space. And so in space, what we're going to be doing is we're going to be using the largest baseline available to Earth. within some reasonable amount of time. And so here's the basic idea. The line of sight to the star changes with time during the Earth's orbit. So this is called using the method of stellar parallax. As you're observing a star during different parts of the year, the background of that star will change. And so if you look at this picture here, let's say that the Earth is right here in its orbit during the month of December, and if you were looking at a star nearby, maybe like a couple light years away, then if you observe this star with a telescope, then you might see this background behind the star. And so now if you wait 6 months later, now in June, then that means that the Earth is now on the opposite side of its orbit. It has traveled about 180 degrees from where it started. And so now you can see the same star, and if the star is close enough, you'll see a significant change in that star's background. And so basically using some simple geometry here, then you can calculate how far away that object is depending on how much the background of the star has changed, okay? And so when we are measuring these kinds of apparent separation distances, of course, when you're looking at the sky, you're not using meters or miles or kilometers. What we're doing here is we're measuring them in their angular widths or angular sizes. So we've talked about this before, but just to review a little bit, when we measure angular sizes, we express them in measurements of degrees, arc minutes, and arc seconds. And so in 1 degree, there's about 60 arc minutes, and in 1 arc minute, there's about 60 arc seconds. And so that tells you that an arc second is extremely small. And just to get an idea of how small things are, if you were able to take your hand and you extend it like all the way in front of you like this, and if you were to measure how thick your pinky is, like using your fingers, that's basically about 1 degree, okay? And so if you were to split up your pinky into 3,600 equal widths, right, that is basically 1 arc second. So it's extremely tiny in the sky. And just to give you an idea how small objects are, here are some angular sizes of celestial objects. So for example, the sun and the moon, they appear about the same size in the sky. That's about half a degree, or basically like half of your pinky nail. And you can do this too when the sun and the moon are directly overhead, or they're highest in the sky. Just take your pinky and then just try to approximate how thick they are in degrees. Jupiter, if you've seen Jupiter before through a telescope, you'll see that it's basically like a point source, or it's a point-like object. And that's only about 30 to 50 arc seconds, extremely small. And so now if you look at Proxima Centauri, then that is going to be the closest star to our solar system that is not our sun. And that is about 1/1000th, or 0.001 of an arc second. So remember your pinky nail? If you divided that by 3,600 equal parts, and you take one of those parts and you divide it by 1,000 more, right? That is basically the angular width of Proxima Centauri. So we're talking about very, very tiny sizes here of objects because they are so far away. So in talking about how can we use parallax and translating that into distance, this diagram summarizes it pretty well. And in talking about parallax, we're going to define this new quantity called the parallactic angle, okay? And so if you look at this figure here, and if we define a line coming from the sun to the star that we're interested in, and we're going to define another line coming from the Earth to the star that we're interested in, well, those two lines are going to form an angle when they intersect, which is going to be at the location of the star. And so the angle between those two lines that I just mentioned is called the parallactic angle, okay? And so you can see here that if the star is close, then the parallactic angle will be this value. However, if you were to observe a star that is further away, then if I shift this object all the way over here, which is going to be this figure on the bottom, then you can see that the parallactic angle is actually smaller. So qualitatively speaking, you can see that the closer the star, the larger the parallactic angle, and the further away the star, the smaller the parallactic angle. So they have like this inverse relationship, okay? So we've standardized it such that when the parallactic angle P is 1 arcsecond, or 1/3600th of your pinky, then the distance to the star, we're going to say, is equal to 1 parsec. So a parsec, you may have heard about it in other sci-fi movies, but the true technical definition is that it is a unit of distance, like a light year. In fact, 1 parsec is actually equivalent to about 3¼ light year. Okay, so that means that when P is 2 arcseconds, the distance to the star is half of a parsec. Okay, so that means, yeah, your parallactic angle got larger, so that makes sense that the star is actually closer to you. And so now we can kind of combine this information and come up with some sort of mathematical expression to discuss or to describe the distance in terms of the parallactic angle P. So if you have some sort of parallactic angle and you say it's in arcseconds, it turns out 1 divided by that parallactic angle P is going to give you the distance d in parsecs. So it's a fraction, but don't freak out. All we really care about here is mathematical reasoning. And we've already talked about that before in saying that the parallactic angle P, the larger it is, okay, then the smaller the distance, which translates in the star being close to you or closer to you. Okay, so that's what we're going for in here. We're not actually going to be plugging in values in here, more about the reasoning and the conceptual idea that goes behind this expression. So in using the parallax method, there are some limitations associated with it, because you can imagine if a star is significantly far away, then the less effective this method will be, because soon enough you won't be able to tell the difference in the background 6 months apart, because that star is indeed that far away. And so therefore the parallax is only accurate up to a specific distance, and really it depends on how good your instrument is. So for example, the Gaia spacecraft, which was launched in 2013, which is pictured here, it looks kind of like a hat or a sombrero, that can measure parallax of about 1 billion stars out of 100 billion in our Milky Way galaxy. And it can measure stars that are up to 300,000 light years away. Okay? So that's a pretty impressive number, actually, considering that our Milky Way galaxy is 100,000 light years across. All right, so I also want to be able to introduce you to the simulation here so you can play with this on your own. I will link this on Canvas, but basically you can see here the parallax in action. So what I have here is the Earth orbiting the Sun. And in this simulation, you can basically change the baseline, or the size effectively of the Earth's orbit around the Sun. And so if we make it equal to the size of the Earth's orbit, which is about 1 AU, right here, and then you can see that in this view here, this is called your telescope view, you can see how much the star is quote-unquote moving because the Earth is orbiting around the Sun. And so, for example, if I were to pause time right here, then you can see that this star will appear in this background of the stars. And if I were to unpause the time and pause it again 6 months later, so I'm going to pause it again right here, now you can see that the star will be appearing in a different background. And so that's when the star is about 6.8 AU away. So that's basically like a little bit further away than Jupiter, which isn't really realistic, but you kind of get the point. And so now if I were to move this star closer, okay, so that means I'm like shifting the location of our solar system here. Let's move it a lot closer. So now let's unpause the time again, see the difference here in terms of the background, how much it will change. So now you're basically seeing this star relative to this background of other stars. And then you'll see a more drastic change because we moved closer to that star, okay? And so just unpausing this and just seeing now there's a bigger, significant motion when you're observing this object relative to its background. Okay, so feel free to play with that, but that's about it for this lecture on stellar parallax. All right, so in the next lecture, we're going to be talking about the brightness of stars and how we describe them in astronomy, which is talking about magnitudes. See you guys next time.